All right, so today I want to start a very important section where we are going to look at the history of the development of our idea of what an atom is. Folks, keep in mind, we're not 100% sure that what we think atoms look like is exactly how they look like. Keep in mind that our symbol for Oak Ridge High School is, of course, the atom model with an acorn in the middle. Okay? Folks, that model was disproven about 70 years ago. We don't think atoms look like that anymore. We like to picture them that way because, frankly, the latest model is so weird that it's hard for us to picture. So this one, picturing it like a teeny tiny little solar system makes more sense to us. But it's not right. And that's one of the things we're going to have to talk about. First of all, who came up with this whole idea of what atoms looked like? Or that there were atoms? Well, 200 years before the time of Jesus, there was an argument amongst Greek philosophers. You have two idiots, the popular ones in the group. The popular crowd. You know what I'm talking about? The in crowd in high school? These guys would have been part of the in crowd. Everyone thought they were cool. Everyone thought they were great. Everyone wanted to be Aristotle and Socrates. Everyone thought they were the coolest philosophers ever. Then there was the nerd. His name was Democritus. Okay? He was the nerd. He was the geek. He was the one that Socrates would come over and pat him on the back. Socrates would come over and pat him on the back, and Democritus would not know that they had put a kick me sign on his back. And they would be wondering, why is everyone kicking me? That's the kind of people that Socrates and Aristotle were. They were mean, they were popular, they were good looking, everyone liked them, and they also believed in this. This is a chair. If you cut it in half, you have two pieces of chair. Cut those half in half, you have pieces of half, 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 half. Now you're at a piece that's so small you can hardly see. You cut it in half, you have chair. Cut it in half with a microscopic little knife, you have chair. Half, half. Now you can't even see it. It's still a chair. That's what the in crowd believed in. Okay? So, the popular boys in school believed it. It's called the continuous theory. It doesn't matter how many times you cut something up, you always have a smaller bit of chair. All right? No one listened to Democritus, who said this: you cut it in half, chair. Cut it in half, chair. Half, chair. Half, chair. Half, chair. Half, chair. Half, atoms. Atoms are teeny tiny little particles that all things are made up of. And every chair is made up of certain types of atoms, and then this desk is going to be made up of different types of atoms, and Emmy's hair is made up of different types of atoms. So when he turned around to explain things, people would kick him because he was a nerd and no one respected him. So, all of these people died. Who did people believe in? Aristotle and Socrates. So for almost 2,000 years, chemistry was the retard of all sciences. People would wonder, look how much biology has advanced. Look how much physics has advanced. Why is chemistry a retard? Why? Because the cool boys believed in the continuous theory of matter. And the nerd, no one listened to.
How do you picture an atom in your mind? Like this, or like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before.
So it wasn't until the 1700s that things started to progress, when scientists realized that nerd back 2,000 years ago, he was right. But it took 2,000 years of us getting over the fact that Aristotle and Socrates were the popular ones, and maybe, just maybe, they were wrong. See what Hank Green has to say.
Well, you aren't shocked, you aren't awed, you might not even be paying attention anymore, but when atomic theory was first proposed, it sounded pretty crazy. And yes, we call it atomic theory, using the scientific definition of theory, which is a well-tested set of ideas that explains many disparate observations, not the colloquial definition of theory, which is a guess. Though luckily there's no one running around anymore saying, atoms are just a theory. But it wasn't that long ago that people were running around saying that, and you want to know who settled it for good? Einstein. Atoms had been postulated for a long time by the 20th century, but it wasn't until Einstein mathematically proved the existence of atoms and molecules in 1905 that the matter was truly settled. And you thought Einstein was all about relativity and E equals mc squared. He also proved atoms exist. Here's how it happened. In 1827, a botanist named Robert Brown was looking at pollen grains in water through a microscope, and he noticed that they jiggled randomly even when there was no movement to cause the jiggling. It was a mystery for a long time, until 1905, when Einstein theorized that this phenomenon was caused by as yet unproven atomic particles actually smacking into the grains of pollen. He wrote up some fancy math, showing that his theory predicted this motion almost perfectly, and everyone had to concede that yes, tiny discrete bits of matter were indeed smacking into the pollen, and thus molecules, and by extension atoms, must exist. Today, we remember this botanist and his discovery by calling the motion he observed Brownian motion. It's kind of crazy that every physical thing you've ever interacted with is made up of little ball thingies. It started with people wondering what would happen if you just kept slicing something in half forever. Eventually, and of course it turns out that there's no knife sharp enough to do this, you end up with one pure unbreakable bit of that substance. The word atom, indeed, is from the Greek for indivisible, though, of course, as we learned in World War II, atoms can be broken as well.
Alright, so what scientist got the ball rolling finally in the right direction? We've already talked about him. He was the scientist that liked measuring everything. His name was Tony Lavoisier. And the law of conservation of matter is the key law that got us going in the right direction. What he discovered is, if you measure how much stuff you begin with before a reaction, you're going to get the same stuff afterwards. He is the first scientist that started measuring things. He used units. He was careful. And he started to discover predictable patterns. Then, a few decades later, this dude by the name of Joseph Proust, he was a French guy, He came to the conclusion that compounds were always made up of the same type of atoms or elements. They had not come back up with atoms yet. They're always made up of the same elements in the same proportion. So water is always made up of hydrogen and oxygen elements, always in the same proportion. Almost 8-to-1 more oxygen than hydrogen by mass. Keeping in mind that oxygen weighed 16 and 2 hydrogens weighed 2. So you see where he got that, but they didn't know anything about hydrogen and oxygen being made up of bits yet. Atoms always combine in the same ratio by mass.
Lavoisier's work was, for a full century, the basis of all chemistry. Proving that you don't have to be rich to get a law at least temporarily named after you, French pharmacist Joseph Proust built on Lavoisier's ideas of extremely careful measurement, showing that a chemical compound always contains the same proportions of elements. For a while we called this Proust's law, but to make it easier to remember for the world, we just call it the law of definite proportions now. And then an English school teacher, John Dalton, followed Proust by examining what at first appeared to be a problem with Proust's work. Carbon and oxygen, when reacted together, would form 2 different proportions, not just one. Of course, what was happening is obvious to us. Carbon and oxygen were reacting to form 2 different compounds, carbon dioxide and carbon monoxide. As Dalton's work continued, he found something truly mind-bendingly fascinating. If you limited the amount of carbon reacting to exactly 1 gram, the mass of oxygen consumed to produce one compound was 1.33 grams, while the mass consumed to produce the other compound was 2.66, exactly double what was required for the other compound. This shook out for other reactions too. When reacting nitrogen and oxygen and limiting to exactly 1 gram of nitrogen, 3 compounds formed. One compound consumed 1.750 grams of oxygen, another consumed 0.8750 grams, and another consumed 0.4374 grams. All of those numbers are relatable by small whole number ratios. Oxygen wasn't reacting with some ephemeral cloud of the idea of nitrogen. It was reacting with individual discrete bits of nitrogen that couldn't be divided. It could react in a number of ways, but it was always the same oxygen and the same nitrogen with the same properties. And so while in our first episode we showed you how Einstein actually proved that atoms exist with super fancy math, Dalton had used multiplication to become the first person to actually have real data supporting the idea of atoms.
Who is the father of the atomic theory? Who brought it all back? His name was John Dalton. He was a Cuban that lived in England at this time. His parents called him Juan. He decided to go by the name of John in order to fit in England. Right? Rwandi, who goes by the name of Randy in order to fit in. Juan Dalton. He was not a Cuban, folks. I'm totally making that up. What law did Dalton contribute, and what does it state? The law of multiple proportions of 1808. When atoms come together, they will always come together in the same whole number ratio. He had rediscovered, because he didn't originally discover them, he had rediscovered the concept of the atom. Finally, things are moving in the right direction. We're starting to learn that we start learning chemistry the right way. People start asking the right questions. This led to the startling discoveries of the late 1800s. Who was studying fluorescence and when? His name was W.K. Röntgen. He studied minerals that glowed when hit by a beam of electrons in the late 1870s. What did we call these beams of electrons? We called them cathode rays. Why did we call them cathode rays? Because the electrons always seem to flow toward the positive side in a battery or a light bulb. That positive side was called the cathode side. This is Roentgen's wife's hand. Very nice hand. This is the first official ever X-ray. The interesting thing, yes, it's her wedding ring. We kind of wonder now, 150 years later, we kind of wonder whether WK was having some marital problems because his wife died a week after taking this picture of unusual but apparently natural causes. Knowing what we know today after the Manhattan Project and Hiroshima and all the stuff that has helped us understand radiation damage, we would say, dang, he killed her because he gave her a whole lot more radiation than anyone would ever give somebody when you're trying to take an X-ray of them. Of course, supposedly, he didn't know. Nevertheless, she died because of his experiment. Here is the dude, one of the fathers of radiation, of X-ray technology. What are cathode ray tubes that he played around with? What are they used for today? Does anyone know? They're called CRTs. CRTs. Old computer monitor and old televisions. Does anyone still have an old school television, the big one, the fat one? That has a cathode ray tube in it. Now, it's not an X-ray. It's not an X-ray machine, but it wouldn't take much alteration in order to convert it into an X-ray. How did Roentgen discover X-rays? He was playing around with a cathode ray tube covered with black paper when he saw a fluorescent material glowing across the room. He theorized that the cathode ray tube was also emitting a type of radiation that was passing through black. Now, what's the significance of it being black?
It's dark.
Thank you. Yes, we've now established that black is dark. Black is an absence of all colors. Why would it be bad for our friend Ben with his black sweatshirt to be out in the middle of summer when it's 98 degrees? Because he would be absorbing all the sunlight. Okay? The reason why we say it's black is because we're not seeing any light coming off of it. So our brains interpret that as black. So he was using black because he wanted to absorb. He wanted to make sure that none of the light from the ambient light, the light from the environment, got into the cathode ray tube. Okay, so he was using black. All right, he was surprised when something started glowing away. So he realized that the cathode ray tube was emitting some rays that were passing through the black paper. Here's an early cathode ray tube. This is a cathode ray tube that has been converted into an X-ray tube by adding a piece of metal. You hit metal, but with cathode rays, it creates X-rays, which are then focused through here. Okay? So what were these cathode rays? Really weird. Let's see how they played around with it. First of all, this was an induction coil. This is just releasing electricity. They would have played around with these in the late 1800s. This is a cathode ray tube. Okay, so this is the energy source. So the electricity is coming out and heading in this direction. And that's why you see the beam of light going from left to right. It's heading toward the cathode side of, the cathode side of the battery, the positive side. All right, so that made them start thinking, watch what happens when you bring a magnet. See how it's deflecting up? That's the positive side of the magnet. So at first they thought this was just pure energy, light. But then when it was starting to be reflected toward the positive side, and you'll see it being reflected away from the negative side of the magnet, they realized can't be energy. Only matter can be deflected. Only matter can show inertia. This was a form of plasma, yes. But they could not conceive that there was anything smaller than the atom. Okay? So this led them to understand that there had to be things smaller than the atom that were negatively charged. Watch what happens when he turned the magnet around toward the negative side. Okay, only matter can do that. So that got them thinking. At this point, this is an X-ray machine. Notice they've got the Geiger counter going. When you have a piece of metal there, you see that metal, that cross? If you have a piece of metal, look at this one. It's spinning in place. What he's doing is he's changing the positive and negative sides. So that's it's making it roll back. But that kind of reminds me of it, doesn't it? That is releasing X-rays. Here's an early X-ray machine. I mean, keep in mind, if you want to become an X-ray technologist, that is a great field. You still first had to become a doctor, because you need to understand what exactly has caused the problem. But then you can work at home and go, hey, there's the break. Radiologists, a lot of radiologists now work at home. They have just really big screen computer monitors, and they get an email saying a new X-rays come in, and then they write a report saying what the problem is. I think this person had 2 problems right there. Can you see where the root canal is?
Yeah. Yeah. Good Lord.
It looks like they're being flipped off, right? Hey, here's where the root canal is! Can you see where all the fillings are?
Yeah.
I think this later X-ray tube. So how far X-rays will penetrate depends on what? It depends on the thickness and the identity of the material. Cannot pass through dense materials such as lead and bone. It is ionizing, high frequency, high energy EM radiation. So, what part did the Frenchman Henri Becquerel play in the story of X-rays? He discovered that certain minerals were giving off things that he thought were X-rays. Further research into X-rays led to what? That some of the rays being given off by such minerals as uranium contain too much energy to be X-rays. Radiation, or what we think of as radiation, had been discovered by Pierre and Marie Curie.
Isn't that what killed her? She died
Eventually, but you know, she died in her 70s, which ain't bad. Now, her husband died when he was a young man, but not from radiation. He was run over by a carriage. So, Becquerel discovered that you take certain rocks and expose them to the sun, and then you place them on photographic film, it would develop the film.
Wow.
What happened was he took that rock, that magic rock, which he thought was absorbing rays from the sun and creating the rays that was exposing the film. What happened is he inadvertently put the rock on some more film and put it in a drawer and shut it off. The next morning, it had still developed the film.
Wow.
Okay, and that led him to think that this rock was giving off X-rays. Actually, the rock was giving off gamma rays, which is a close cousin to the X-ray, and still was doing the same thing to the photographic film. Why do we not use gamma rays?
They can kill you.
Because gamma rays are even more dangerous than X-rays.
What kind of rock is that?
Pitch blende had uranium in it. What scientist was responsible for the discovery of two parts of the atom? What type of rays did he work with? His name was J.J. Thomson. He studied under these characters, Marie and Pierre Curie and Becquerel, and used the cathode ray tube to come up with the next model of the atom.
Was why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. It's basically what a neon light is. Because this light was originally produced by a negative electrode, or a cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English dessert, plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next
What atomic model did Thomson propose? The plum pudding model.
Sounds nasty.
Well, it's kind of like banana pudding, except that the English, and to call it pudding is also kind of weird because it's cakey. It has a bunch of raisins in it.
Ugh.
So I like to think of it as the banana pudding model because I love banana pudding, where the vanilla wafers are electrons and the banana pudding part is the positive goo. So no longer do we believe at this point that the atom is indestructible and made up of tiny little particles. We now believe that the atom is made up of at least two things: a positive goo and negative raisins. Negative raisins. Here's yet another model.
Looks like a dinosaur.
Thomson introduced his model in 1804, a sphere of positive charge with electrons embedded in it, called the plum pudding model. Here is Thomson with his cathode ray tube right there.
Did he die?
Yeah, he's dead.
Of like radiation?
Most of us die of radiation, but he was an old guy. The Curies at this time were exploring this funny energy being given off by certain rocks, radiation. They were the pioneers of radioactivity. They messed around with the mineral called pitch blende. They also discovered two other elements that gave off radiation. Polonium. Guess what polonium was named after? And if you think it's Polonius from the play Hamlet, you were wrong.
Polynesia.
Polynesia, because Marie here that you will see looks Polynesian.
Are you serious?
No.
Get her.
I really
get her.
thought I was
Get her.
Okay, is there another European country that sounds like Polynesia?
Poland.
Poland.
But it'd be polonium then. Polonium.
Well, polonium is named after her native country of Poland. Radium is named after
Radiation.
radiation. that famous European country. Radiation. Okay, here is
I mean, I don't look
good-looking Marie.
She does look Polynesian.
And this is her when she's old. Her hands were gnarled from radiation exposure. She died old, but yeah, she probably died from years and years of exposure to radiation. You can go to France, to a university in France, and actually see her notes. She kept meticulous notes, and you can see her notebook where she actually wrote the notes on what became the very beginnings of our understanding of radiation. Okay? It is inside a piece of glass that's several inches thick. Why? Okay, I don't think people are that concerned with stealing. Okay, if you steal it and put it in your back pocket, you may die several weeks later. Okay, this sucker is so radioactive. This notebook is so radioactive because of years of her playing around and making notes with it, that you would actually have to wear a radiation suit in order to hold it.
A book? A
Can we do that?
A notebook. Yes, let's all go to France and visit this notebook. So, why would she have done that? Why would she play with this stuff? It was so dangerous.
For knowledge.
She didn't know. Shoot. I mean, there are pictures of the Manhattan Project people working on stuff that modern radiation workers would go, you know, why aren't they wearing a suit? Because they didn't know back then. People had to die in order for us to figure out that this stuff was dangerous. This is her husband. He may have been able to die of radiation poisoning if he had not been run over by a horse-drawn carriage. This is J.J. Thomson when he was old and gray. What scientist was responsible for the discovery of the nucleus? His name was Ernest Rutherford. Ernest Rutherford. Rutherford.
Big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium, they were positively charged, and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area, an area that he called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles, protons. Now we're getting close to reality.
Okay. Keep in mind, he was trying to prove that his teacher was correct. And he ended up proving that his teacher was oh so very wrong. This is his assistant, Geiger. You may know him as the Count from Sesame Street. That's why he's called Geiger Counter. Get it? From Sesame Street, you know, in the middle of the night they would find him going, one beaker, two beakers, Get it? The Geiger Counter.
That show's really annoying.
Geiger Counter. Oh, man. The Count from Sesame Street. He used to count things.
Was he the vampire
I was
guy?
saying that Geiger Counter
I thought
is
he
the
was Dracula.
I thought that was Dracula.
No, he was this guy. Geiger Counter
Yeah, I was
is
Dracula.
I thought it was, I thought it was
okay.
vampire.
He was Dracula, but
Alright then,
I
alright.
thought it was funny because the Geiger Counter. It's a device used to measure radioactivity. And then I connected it to the Count, who was also German.
It's not working out for you.
Oh my gosh, it's so funny.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large.
If his teacher was right, it should have all been going through it, because there should not have been anything large enough to deflect it. By the fact that there were deflections meant that there was something wrong with that.
Angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low-mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so now let's make sure that we are able to draw the different atomic models that we have been dealing with. This is Dalton's atomic model. It's called the solid sphere model. Solid sphere. You will be tested on this. Good, thank you. Some people are writing now.
Oh.
Then the Thomson model is called the plum pudding model. Anywhere, I don't care. Anywhere in your notes. So if you're there in YouTube land, you better be drawing this somewhere too. That is the plum pudding model, where the vanilla wafers are the electrons, the raisins, really. I don't know why they call it pudding. It's like a cake. Of course, they call biscuits cookies. No, we call them cookies. They call them biscuits, right? Now, the nuclear model is Rutherford's. Rutherford. And it has a nucleus with the electrons surrounding it. He's getting closer. Rutherford theorized that if the plum pudding model was correct, the number of positive and negative particles in an atom would be the same, with the particles evenly spread within the atom. The result was completely unexpected. By Rutherford and his assistant Geiger, who actually performed the experiment, Rutherford was forced to rethink the model, realizing that the only explanation was that all the positive particles must have been together in a nucleus. The gold foil experiment is an important point.
Dear mother, we gotta write all that?
Yep.
You know how large my handwriting is? What is it?
Use a smaller font. Alright guys, I'm going to go on. You can always get it on YouTube. Describe the model as developed due to the experiment. Whatever the positive alphas must have hit must have been very large and very positive. The Rutherford model was proposed. The atom had a positive nucleus with a negative electrons orbiting around it like planets around the sun. There it is. Alright, a couple years later, a Great Dane, no, not the dog, Niels Bohr, gave us the next model of the atom. His electrons weren't just hanging out, they were moving around the nucleus, but not in stable orbits like we would think of planets revolving around the sun. Let's have Hank Green introduce Niels Bohr.
These chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculation positions based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways.
All right. So, what can we say about Bohr's model? Electrons do not stay in their orbit, not like the planets. When they gain energy, they move further away.
Wait, how do you say his first name?
Niles.
Could you say Niels?
Niels, maybe. You can. Niels Bohr.
Got a ring to it.
This is called excited state. When they lose energy, they go back to their original orbit, ground state. The energy can be any part of the EM spectrum. The way to remember this is by thinking of Kelsey. The day that Kelsey got from her rich uncle $100, and he told her, all right, girl, you have to spend it. If you don't spend it, I'll never give you any money ever again. Don't save it. I know your tendency is to want to put it on a high yield interest savings bond and save it for college, but I don't want you to do that. I want you to go to as far away as $100 will take you and spend it, Kelsey, because I love you and you're my favorite niece. Okay, so how far will you go? Well, how far can first of all, are you going to be excited, or are you going to look like you're really bored and ignore your uncle? Really? You're not going to act excited? Okay, well, you're no longer in the analogy. All right, Bailey, are you going to get excited? Yeah? Are you gonna, you're gonna get really excited and hug your uncle, and then where are you gonna go?
Down the street. $100 won't get you far, man.
Turkey Creek or the mall? Turkey Creek. Turkey Creek. So she goes to Turkey Creek. That's pretty far. If he had given her $1,000, then maybe she could have gone to Atlanta or Nashville. All right. So here's her parents. Here's she, because she's normally very, very poor and can't afford to go anywhere. And now she has blinked away and she is in Turkey Creek. Okay? But does she stay in Turkey Creek? No, because if she's going to go to Turkey Creek, she's going to spend money. She first goes to Old Navy, where Old Navy has bought up a bunch of old jeans that people have turned into Goodwill. They have cut holes in the old jeans. They have dragged the jeans behind a truck for 2 miles. They've washed the jeans. Then they've put all the made in China tags and all that stuff, because all the cool stuff is made in China. And then they are ready to sell it to her for $45. They bought it at Goodwill for $2. The truck driving cost them maybe a couple bucks. That's $4. And then the person, the migrant worker that's cutting up the jeans with scissors, pay them. Yeah, because, they're illegals. They pay them, $2 an hour. So that's probably another 30 cents worth. So they spent $4.30 on those jeans, and they sold it to you for $45, and you bring them to school. That is a profit. Okay, so you spent $45. You now have $55 left, and you are now closer to your parents because you're running out of money. Okay? So, in order to go from here to here, you had to spend $45. Then you're hungry, so you go to Five Guys Burgers and Fries because you are so skinny you need to gain some weight. So Five Guys Burgers and Fries. Yay! Get the big burger, not the little one. Get the big burger and the big French fries, which they put it a little bit in a little cup, and then they just throw a whole potato in there. Oh! Oh, that is so awesome! I'm so hungry now.
Yeah, thanks.
Five Guys Burgers and Fries, and you can get everything in black. I mean, you can go with the jalapenos. I don't like those, but get the slimy onions. Those are good. And then, okay, so that's about $8 or $9. So now she's a little bit closer to her parents. Okay, every time she spends money, she gets a little closer. Then Menchie's. She got to go to Menchie's, get some dessert. Okay, and that was just a little hot because she just spent a little bit of money there. And then she goes to GameStop.
And it's gone.
$35, and she spends the latest Pokemon game. $35, Pokemon Smash Brothers. Something.
What are you doing?
I don't know. I hear my sons talking about this. So,
You're mixing fan bases.
What is that?
You are though. I mean,
I don't know. She just spent $35 on a video game
Pokemon.
because she and her boyfriend want to play Game Boy together and like DS, PlayStation DS. What's the little one that they play?
Game Boy.
Okay, whatever. She wanted to play with her boyfriend Smash Brothers Mario thing. Okay, so
Oh my god.
I just explained to you the Bohr model. In the Bohr model, Bailey, i.e. the electrons, will gain energy and go into excited state. They don't stay excited for very long. They will lose energy in different steps. If they lose a little bit of energy, it's going to be a certain part of the EM spectrum that will be shed by that electron. If they lose a lot of energy, it's going to be on the left side of the EM spectrum. So let's review. You've got gamma rays. You've got X-rays. You have UV, and those are what we call the ionizing. Danger. Then comes visible light, and I always have to do it backwards. Violet, indigo, blue, green, yellow, orange, and red. Yay, I did it.
Roy G. Biv.
Roy G. Biv. Okay, and then comes infrared, microwaves, and radio waves, and that's what our cell phones emit. Okay, so when she was at Old Navy, she probably gave off light in the UV range, so we didn't see it. When she was at Five Guys Burgers and Fries, she may have given off red light. Okay? When she was at Menchie, she only spent $5. She might have given off microwave light, in which case we would not have seen it. And then when she went to GameStop, she could have very well given off indigo light, because that was a good chunk of the money. So, on your way down, back to ground state, electrons are going to give off light at various parts of the EM spectrum. The bigger the jump down to ground state, the more on this side, on the high energy side, the high frequency side, you'll give off light. The smaller the jump, the more on this side you'll give off light. So whenever you see light, what you're seeing is the evidence of electrons going into excited state, then going back to ground state. Those lights back there are emitting mostly in the visible light range. These fluorescent lights, mostly in the visible light range, but some of it in UV and some of it in infrared. When you guys use those remote controls, you are exciting electrons, millions upon millions of teeny tiny little Baileys going crazy, but only spending a little bit of money because the light that you are hitting me with is in the infrared range. In the infrared range. And you've got this little infrared eyeball here that detects light. The physics teachers, they have ones that go in the radio waves, and you don't need a sensor like this. It's just a radio, it's a radio communicator. So you have a radio receiver, so they don't have to be aiming it in this direction. They can just aim it in any direction. All right, let's have this wonderful Indian lady explain what's happening with Bailey.
While revolving in discrete orbits, electrons do not radiate energy, and so the atom doesn't.
Okay, so she does not spiral down. She doesn't go to Turkey Creek and then start running back, giving off money all the way back. Okay, she will actually go to Turkey Creek and spend money in different spots, and each spot getting closer and closer to Oak Ridge.
Collapse. The state of an atom with lowest energy is known as the ground state of an atom.
Okay, so this is going to be Bailey. She's as close to her parents as she can possibly get because she may love them, but she doesn't love them that much at this age. She'll grow to love them more once she has kids of her own. Okay, now we're going to give her some energy. Watch.
Energy is gained.
Oh, so she went all the way to Turkey Creek. She got as far away from her parents as she could get. $100 is not that far. But can you imagine if someone gave her $100,000? That's like ionization energy. What would happen? She would leave. She's gone. She would become an independent agent. And that's what ionization energy is. When an electron gains so much energy that it leaves the atom. It leaves the atom. Now, is she going to stay excited for very long? No. She's a typical teenage girl. Money comes in, money comes out.
Or lost by an electron when it jumps from one orbit to the other.
What do you
The
call
atom
that?
is then said to be in the excited state.
And then back down to ground state. Now, believe it or not, whenever you see a light bulb, that's exactly what's going on. This is an awesome, awesome animation. It's Australian.
Contrary to popular belief, the original light bulb was not invented by Thomas Edison, but Sir Humphrey Davy in 1809. Creating the first electricity-powered light, the invention was greatly refined 60 years later by Edison, designing a powerful bulb that could burn for up to 40 hours. This was the first incandescent light bulb. To understand it, we first have to recognize light at an atomic level. At its most basic form, light is seen as a series of particles called photons. They are created as excess energy packets when an atom's electrons suddenly gain and lose energy. When an atom is energized, its electrons shift further away from its core. When the energy stops, the electron returns to its natural orbit, releasing built-up energy as a photon. By repeatedly energizing atoms, it's possible to generate a steady stream of light energy. In a light bulb, the energy source needed to energize the atoms is provided via electricity traveling through its base, electricity simply being the movement of free electrons. The key component that made Edison's design so groundbreaking was the filament at its center. Being the most important part of a light bulb, it's the size of the filament that determines the intensity of the light emitted. In an everyday bulb, the filament is about 50 centimeters long, but is coiled down to a smaller size, then coiled again, leaving a 2 to 3 centimeter piece in its place. Tungsten is usually chosen for its extremely high melting point. Electrons burst through the filament, but because it's so tightly coiled, they'll frequently fly off and bump into each other, causing the filament to light up and become extremely hot. All this takes place inside an airtight bulb. If the reaction were to take place in open air, the heat generated would be enough to ignite the surrounding oxygen, destroying the filament. However, in a vacuum, when the filament is heated, the vibrating tungsten atoms occasionally break off. If enough do this, the filament splits and the light bulb is broken. To counter this, the empty bulb is packed full of an inert gas such as argon or krypton. With the gas, any atoms that break off bounce off the gas atoms and rejoin the filament, effectively quadrupling the bulb's life. Although incandescent light bulbs are a staple of modern technology, they've been proven to be very inefficient. An everyday light bulb produces about 20% visible light, with 5% released as light outside our visible spectrum, such as ultraviolet and infrared. The rest is produced as heat, leaving the bulb red hot. To counteract this, the fluorescent light was invented, Using an entirely different process, it's 5 times as efficient at producing light. This will be discussed in a later episode. There are 3 main components to an incandescent lamp: the free-moving electrons traveling through its base, the airtight gas bulb filled with inert gas, and the tightly woven tungsten wire at its center. All working together releases...
Because light bulbs like these are so inefficient, and because our government is so inefficient, our government has decided to outlaw incandescent light bulbs. They've been slowly phasing them out from 75 to 60 watt to 45. So I think this year 45s get done away with. This will be, I think, maybe the last year of 45s. So because of that, and because for the last 120 years incandescent light bulbs have been working so well, I have stored a lot of these things, because I know that at some point those curly Q fluorescent light bulbs are going to be determined to be harmful to us. Have you ever broken one of those?
Yes.
Look it up on the internet what you're supposed to do. You're supposed to evacuate everyone from your house, and then you're supposed to call the hazmat team to come and dispose of it. Yes, that is scary. That's why we've gone to, we're using incandescent when we can, but we're slowly buying the LED light bulbs, which last even longer than the fluorescent light bulbs and are safe. They don't contain teeny tiny amounts of mercury. Okay, so if by chance you see me in the park one of these days wearing a trench coat, then no. If you want to buy a incandescent light bulb, come to see me, because, you know, I'll be there with my hat and my trench coat, and people are going to be coming up to me going, hey, do you have a 60?
Are you
Do you have
gonna
a 60?
open it, like,
And I open up my trench coat, I go, I have several 60 watts. So I give them a 60 watt for $5 or $5. Cost me 35 cents, $5. That's pretty good.
Yeah.
My fear is that a cop will see me, I'll have to run for it and fall and smash all my light bulbs. That could be kind of painful if you've got a trench coat full of incandescent light bulbs that are broken inside of your stomach. Okay, so how do the curly Q works? The curly Q are basically smaller versions of these guys, the fluorescent light bulbs. All right, they still work on the same principle of exciting electrons, and those electrons going into excited state, then coming back down, and when they come back down, they give off light.
The basic principle of operation in a fluorescent lamp is simple. You have a glass tube, and inside, all you have in the tube at each end are electrodes called cathodes. And in the case of the hot cathode, they're like a little filament. That's why you have two pins on each end, because each pin goes to one end of the filament. And these filaments inside are electrodes that send current through the gas in the lamp. The gas in the lamp is argon, and there's a little bit of mercury in the tube, just a tiny amount, like just a pinhead amount of mercury. And how it works is when the current is switched on, these cathodes heat up, and they're coated with a special material that gives off electrons. It works on the same principle as a vacuum tube, and it's called thermionic emission.
So when those electrons, they're going to build up on either side, and then they are rocketed over to the other side. As they do that, they crash into other atoms, and they excite those electrons. And it's mostly the mercury electrons that do all the work. They will release light. Actually, the light they release is ultraviolet light, which is dangerous to us. But fortunately for us, you notice that there's this white powder on the surface of the curly Q and these guys, and that white powder is called phosphor. And the phosphor will absorb the UV light, and then its electrons go into excited state and release light that is in the visible light range. So without that stuff, then these things are very dangerous, because they're giving off UV light that can cause cataracts in your eyes, that can also cause skin burns. So we're very grateful. So the way it is right now, it's giving off ultraviolet light.
Heats up, it gives off electrons. And that's good because when the filaments heat up, they give off the electrons. Then a high voltage pulse is sent through the lamp from the starter, and that pushes those electrons through the lamp from one end to the other, and it starts an arc through the lamp, through the gas that's in the lamp, which is argon. And this argon arc makes enough heat to vaporize the mercury that's in the tube, and that goes into the arc stream and produces ultraviolet radiation, ultraviolet light. And the ultraviolet light hits a powder on the inside of the tube. That's why they're white. It's called a phosphor. And it's a material that glows when ultraviolet radiation strikes it. So when the UV radiation produced by the arc through the gas in the lamp hits the phosphor, it makes it glow, and that's what produces light.
So if you've ever been in a tanning salon, you've encountered these fluorescent light bulbs without the phosphor, or with limited phosphor to allow some of the UV to come out and burn your skin and cause skin cancer. Okay, so what is the modern theory of atoms called? It is called the quantum theory. So Niels Bohr, let's go back and review. You've got, what do we call Dalton's model? Solid sphere. What do we call Thomson's model? Plum pudding. What do we call Rutherford's model with the electrons outside? The nuclear model. And now we have Bohr's model, which should look familiar to you. That's the one that probably has been taught to you since middle school, but that was disproven back almost 100 years ago. We no longer believe in Bohr's planetary model, the planetary model. Okay, we believe in the quantum theory. What does the quantum theory state? Watch.
But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know! All the people I've mentioned and many others put their heads together over time to build this current and, I might say, quite elegant understanding of atomic theory. Now, after 2,500 years, even though we can't see them, we can know what they're like and how they work because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right. Scientists in Bohr's day fully believed that the planetary model was right, and today we're extremely confident that the quantum model is correct. But it may not be all the way correct, and that's where you come in. The only way we can go on being sure is to keep asking questions and conducting experiments, and that's why you're taking chemistry and physics. Pay attention.
All right. So, list the ways the atomic model has changed since the turn of the century. Electrons are not really orbiting. If you take out your notes page, you'll see that it's just... B, the nucleus itself is composed of two different types of particles, protons and neutrons. Neutrons have no charge, protons are positive. They are much larger than the electron. Most of the atom's mass is taken up by the protons and neutrons. The nucleus takes up 1/10 of the diameter of the atom. The rest is the electron cloud. What?
What's the second one for A?
Location. Location, location, location. All right, so let's review. First model. Who? What do we call it?
Solid. Yep.
Who? Then came
Raisin bread.
plum pudding.
Does that matter? Like we have to know.
Yeah.
Oh.
Name.
Yeah.
Then came
Nuclear model.
name. Experiment that he used to prove it. Next. No.
Bohr.
Bohr. What do we call it?
No. Planetary.
Planetary. Then finally, you've got a nucleus with electrons, most of them really close to the nucleus, with some electrons further and further away. This is called the
What the?
cloud model. And who proposed it? Well, we don't have a name. We have a group of scientists.
We're going to call them the TMNT.
Oh, okay.
The quantum theorists. And then the final, most modern model has the protons found in two discrete areas with the neutrons found away from them. And then you have electrons orbiting back and forth, but not all the way around it. It's called the smiley face model, and I'm proposing it. It is my theory, and you can't prove it, that it's wrong. The smiley face model. I think it's the happiest of all the models.
True. Pretty reasonable. Very reasonable.
All right, so let's tie it all together. What are isotopes? Give some examples, because we learned in the early part of the 20th century that not all atoms were exactly the same in an element. Dalton thought they were, but we have proven that that is incorrect. For example, carbon comes in at least two flavors, carbon-14 and carbon-12. They are both carbon because of the number of protons. Their neutrons are going to be different. That's how we come up with 14. 8 plus 6 is 14. 6 plus 6 is 12. You wow me, but wait till you miss it on the quiz here in 5 minutes. Fluorine-19 is made up of fluorine, which is 9, and 10 neutrons. 10 plus 9, 19. It's fluorine, but it's still number 9. In order to be 20, it's going to have 11 neutrons. So we've heard the name. I heard the name mentioned several times in the movie Godzilla, or Godzilla. And what are radioisotopes? Okay, these are isotopes that will be minding their business. Who did we use it as an example of a radioisotope? Oh, Serenity, that's right. She was a radioisotope. She will undergo many, many decays until finally she stabilizes and becomes a non-radioisotope. A radioisotope is any isotope that is unstable and tends to decay, releasing radiation in the form of particles and energy. How many elements have isotopes? We used to think only a few. Actually, now we think that most elements have isotopes. How does this present a problem to the periodic table? Well, since there are various flavors of each element, that means their masses that are on the periodic table have to be an average. Not just an average. It's called a weighted average, because they not only take in consideration all the different masses of all the different isotopes, but how plentiful they are. How plentiful they are. So it's kind of like, if you guys have a class where everything's worth the same amount, but at the end the teacher says, well, tests are 40% of your grade, and homework is 30% of the grade, and then your essays are 30% of the grade. English is like that. Well, that's how I do a straight average. Okay? Because what I do is I make the test worth 100, and labs worth 40, and quizzes worth anywhere from 3 to 10. Okay? So I give the worth by narrowing down how many points they're worth. Your English teacher may make everything out of 100, but then go back and give your test more worth, and they do that by multiplying the percentage of what it is, like 40%, they multiply 0.40 into the total amount of points that you've made there. So your total points are made up of 40% of your test. What did Marie Curie originally think about isotopes? She thought that only large atoms were radioactive. And she was extremely wrong. Virtually all elements have a radioisotope, a serenity cousin. And here's this lady working with a radioactive substance. I know she is because of the shield. And that's the next thing we're going to talk about. We're going to talk about all the bits and pieces that serenity will give off when she decays. Well, yes, in our analogy, but in reality, it can be either alpha, beta, or beta, as the English call it. Alpha, beta, positron, high energy neutrons, all sorts of bits and pieces that can come off of you. All right?